Hi, I'm Daniel, a PhD student from the University of British Columbia. We present neural bilateral filtering, an iterative algorithm for top-down instance segmentation on point clouds. This is a joint work with Weiwei, Renjie, Vladimir, Soroosh, Kwang, and Andrea. We introduce an iterative layer we call neural bilateral filtering. Our method is inspired by traditional bilateral filtering, a well-known image processing technique. Our algorithm generates query conditional instance proposals for the 3D point cloud and achieves state-of-the-art 3D instance segmentation results compared to other top-down methods. The layer takes a query point sampled from the point cloud as input and outputs the instance proposal in the form of an affinity map. As an iterative layer, neural bilateral filtering iteratively refines the affinity map. A common way that existing methods generate instance proposals is to directly regress the bounding box, outputting the proposals from a following segmentation module. This bounding box regression is widely used in 2D top-down instance segmentation, leading to the successes of top-down methods in the 2D domain. However, the success for 2D top-down methods does not carry over into 3D instance segmentation benchmarks, where bottom-up strategies dominate in performance. In this work, we argue that bounding box regression bottlenecks the performance of top-down 3D instance segmentation. We validate our findings on simple synthetic 2D point clouds that are composed of lines, circles, and background points. As we can see here, the bounding box regression does not produce sufficiently accurate proposal boundaries. As a result, its MAP performance is less than 50%, while our method achieves nearly perfect results with MAP above 90%. Our method takes a query Q sampled on the input point cloud and outputs an affinity score map, ranging from 0 to 1. In order to isolate instances, we combine spatial similarity and semantic similarity. We determine that two points belong to the same instance if they are close to each other, both spatially and semantically. We multiply spatial similarity and semantic similarity to get the final affinity score. We implement semantic similarity using the simple exponential kernel with a temperature parameter. Specifically, given a query Q and the nth point, we apply an L2 distance kernel on the semantic features for n and q extracted from the backbone. The Gaussian kernel is commonly used in traditional bilateral filtering, as it generates isotropic spatial affinity. However, it's often impossible to place a Gaussian kernel to separate two instances of the same semantic class. To avoid this issue, we employ a non-isotropic kernel for spatial similarity, which is able to isolate the queried instance from nearby instances of the same class. As with the semantic similarity, we use a temperature parameter to control the kernel smoothness. We parameterize the non-isotropic kernel with a hypercoordinate network that predicts a convex hull consisting of a set of hyperplanes. These hyperplanes together partition the physical space into two parts, which are inside or outside the queried instance. For points inside the convex hull, the network outputs 0 distance, while for points outside, it gives the L2 distance relative to the nearest face in the convex hull. The hypernetwork is a small and efficient MLP, which predicts these hyperplanes from the query point's feature vector. Using the affinity score definition, we iteratively update queries as the weighted center of all other points. This allows us to shift queries into the centroid of corresponding instances to refine the shape instance proposals. We show on both 2D synthetic data and 3D real point clouds that we can learn high-quality convex hulls. On the left, we show consistent convex hulls predicted for different queries sampled on the same instance. On the right, we show that we can learn convex hulls for different complex objects. We first demonstrate the performance of our method on synthetic data. We see that bounding box regression bottlenecks the performance of instance segmentation. Even on this very simple dataset, it's still hard to get satisfactory performance with bounding box regression. Its MAP is less than 50%, while our method gives near perfect performance. We further validate our pipeline on the real ScanNet benchmark. Our method is the best among purely top-down methods. However, the top-down methods in general lag behind those using a bottom-up strategy. Regardless, our work shows how bounding box regression bottlenecks top-down instance segmentation and demonstrates how this can be avoided. We believe there is much potential for improvement in top-down methods for 3D point cloud segmentation, which could help bring them closer to the impressive results they produce for natural images. Thank you for listening. For more results, please refer to our project website.